Let's talk briefly about the definition of a definite integral and how to evaluate the value of one of these when it's written in its most pure elemental form. So this definite integral is not a function of x. When we evaluate it from 4 to 32, it'll be equal to a constant. It's just a value, not a function. What is its value? Well, it depends on the actual definition of a definite integral of a function from 4 to 32. Its definition is that it's a sum of areas of rectangles. So in this case, it might be the sum of these 7 rectangles. And it's estimating the area under the curve of the cubed root of 2x from 4 to 32, from here to there. So for each rectangle, its area is its base times its height. And if we did this for each rectangle and added them all up, we'd have the sum of the areas of the rectangles, which in this case would be an overestimate of the exact area under the curve, which is what we know this represents. And we can get the exact area by taking the limit as the number of these rectangles approaches infinity. So as the number of rectangles approaches infinity, our counters will go from 1 to n, which is approaching an infinite number of rectangles, each rectangle's area being base times height. The base of each rectangle will be, we'll take this domain from 4 to 32, and we'll divide it up by n rectangles. So each rectangle's base is 28 divided by the number of rectangles. And now what about the height? The height is the vertical dimension, which is the y value, which in this case is defined by the cubed root of 2x. But every rectangle's height is determined by the x value, specifically these x values, there, and then there, and then there, 20, 24, 28, 32. We have to place these x values into the function to get the y value, which is the rectangle's height. You can see for this first x value, the y value will be here, this high, 2.25, which is the height of the rectangle. For the second rectangle, our x value has to be 12. When you put a 12 in, the output, the cube root of 2 times 12, will give us this y value, the height of that rectangle. So the easy part of the height is that it's just this y value. The hard part is what expression goes in here so that when I is 1, we'll get 8 for the x value. So that putting it into this gives us the y value. And so when I is 2, we need to get an x value of 12. When I is 3, we need to get x value of 16. When I is 4, our x value needs to be 20, etc. So what goes in there? We'll notice that the very first x value, this dot, was our starting point plus the width of a rectangle. And the second x value, which we'll put in to get our height of the second rectangle, was start value plus the width of the rectangle twice. Did you see the correlation between I being 2 and going the width of the rectangle twice? To get the height of the third rectangle, when I is 3, it's going to be start value plus the width of the rectangle once, twice, 3 times. That's how we'll get that x value that we'll put in to get the height of the rectangle number 3. So the input here has to always be the start value times the width of the rectangle I times. In other words, each rectangle's area is base times height, and the height is the y value from our y function, and the x values have to start at the lower limit of 4, and then we're going to add the rectangle's width I times. There it is. This is the definition of the definite integral from 4 to 32. It's the sum of the infinite number of rectangles where each rectangle's area is base times height. And the height came from the function for the y value, and the input had to start here and add the width one time when I was 1, 2 times when I was 2, starting here and add the width 1, 2, 3 times when I was 3. Those gave us the x values, which are in these black brackets, and when you multiply that times 2 and take the cubed root, you've got the y value, height of every rectangle. There it is. All right, so we can apply this problem now to a question from the practice exam like number 3. Of course, if a problem began like this, it might seem much more difficult than number 3. But immediately we notice that it looks like a product. It's probably going to be rectangles. This is probably going to be a Riemann sum. We're probably going to want to just determine what definite integral in this notation is this equal to, because this is the definite integral. This was just a nice result from the fundamental theorem of calculus that helps make this process so much easier. So we see this and we think rectangles, base, and height. Let's start with that base. We can see that the upper limit minus the lower limit is the range of those x values, and when you divide by n, that's the width of each rectangle, the base of each rectangle. So the distance from the upper limit of integration to the lower limit of integration is 28. And then we come over here and we can see that the input starts at 4 and it's adding the width I times. So we're starting at 4, which means we must end at 32. So we know immediately that this is going to be a definite integral from 4 to 32. Now the width of the rectangle ends up being the dx in our problem. So we just need an expression for the height of the rectangles, which will be the y value, which we can see is the cube root of 2 times our input. And just like that, we can evaluate this Riemann sum by just converting it to this notation and then using all the great fundamental theorem of calculus stuff to do this really quickly and easily. Let's take a quick look now at number 3 from the practice test. If we expand when k is 1, 2, and 3, we can see that these are all rectangles whose widths are 1 over n. So from the lower limit to the upper limit of integration, if we divide that span by n rectangles, we get the width of each rectangle, which is 1 over n. So that means the distance from the lower limit to the upper limit must be 1. All right, that brings us to the height of the rectangle. Since there's nothing being added, it must be the case that we're starting at 0. And then we add the width k times. So when k is 1, we start at 0, add the width once, and that gives us this x value, which we can then put into the function, which is just square root. So we go 1 to the end to the right, put that in, and the output is the height. And the height was just the square root of 1 over n. And then for the second rectangle, its width is also 1 over n, but its height is going to be the y value, which is the x value, which was 0, plus the width twice. That's our x value. We put it into the function, which gives us our output, which is the height of the rectangle. And it was just the square root of 2 over n. So the function must just be the square root of x. And this expression, therefore, must just be the definite integral from 0 all the way up to 1 of the square root of x dx. And so we can easily find that value by doing the antiderivative, evaluating from 0 to 1, and we get 2/3 minus 0, or just 2/3.